So, welcome to my course C-based VLSI design. I am Dr. Chandan Karfa. I am with IIT Guwahati. I am going to teach this course to you. So, let us try to understand what is C-based VLSI design. So, what is VLSI? VLSI is something is the process of creating integrated circuits by combining million of transistors, right. So, when you try to build a chip or IC with million or billion of transistors, that is VLSI, right. And then why, so the question is why, that how we will build a chip with millions of transistors, right. Is it manually, is it possible to develop such such chip? It is answer is no, right. So, how can you build a chip manually by just doing all things manually? It is impossible. So, how it is being done, right. So, how it is done? We need automation, right. We need some software that will do things for us, right. So, we'll give some specification, and the automation tool will basically do the whole things for us and will give the integrated circuits finally, right. So far we understand that what is IC and how this VLSI chip is built with the help of electronic design automation tools. But this course asks the question, can we start this process from a C code, right, or a high level code? It can be C, C++, Python and all, but can I start this design process from this C? It is particularly very challenging because once you think about the hardware, right. So, it is basically it has a clock, reset, set, it has some synchronization, asynchronous clock, so many things are there, you have to always take care of everything, right. So, it is basically is completely different design paradigm, whereas your C, which is untimed code, there is no clock there, right. You just write a code which is just execute top down manner, right. So, top to bottom manner. So, there is no clock involved, there is no adder, multiplier, RAM, ROM, nothing, right. So, the question here is that can we develop a software, a automation tool that will just take a C code and it convert to a hardware for me. It is kind of a gateway from a software code to hardware. So, it is particularly very exciting, right. Then in all this trouble, all this complexities of developing a hardware is something we can eliminate, right. So, that is why this course is so exciting, and I am sure that if you went through this whole courses, you will also be very excited and you will learn lot of things. Okay. So, in this particular course, I just try to motivate you why this this electronic design automation is so important, how this IC revolution comes, and how this particular C based VLSI design, particularly in the current context, is so important. And then I am going to conclude this course with the topics to be covered in this course. Okay. So, let us go back to the time 1958 when the first transistor was built, right. So, this picture is shown there. So, this was the first transistor built in 1995 in TI, right. And so, you can understand the size of this transistor, and now this 2020 is a 20-year-old picture. It is a Pentium 4 processors which consist of 42 million number of transistors, and the size is you can understand, right. So, a processor say. So, you can understand this revolution, right. So, from a tiny single transistor which is something is almost 2 centimeter long, wide, which is actually now we can actually pack millions of transistors into a very small size of die, right. So, I mean there are some other funny pictures here. This is the supposed to be the first computer. You can see this is the size of this computer, which is measured in cubic feet, right. And now we have this static strain which comes in I think 2018, which is has 30 billion transistors, right. So, you can understand the growth in 50-60 years, the kind of growth happened in this electronics in industry in the span of 50 or 60 years. So, here is the chart that give you this kind of this growth chart kind of. So, usually we have the number of transistors in K mentioned in this y axis, and this is the year. So, you can see this 8086 have something 15K kind of, or say 20K kind of transistors, and now in 2012 and so we reach a target of 1 billion transistor in a single chip, right. So, this something is just highlight the kind of the growth or the evaluation of this IC, and whenever you have more things, you have more trouble, right. So, the complexity is growing, right. So, this is where I just taken certain the modern processors, say Apple A11, it has 4 billion transistors, this IBM Power 9 has around 8 billion transistors, and this NVIDIA this processor has around 21 billion transistors. So, that you understand the complexity that the current electronic design transformation tool to handle, right. So, now the question here is it how to design this 10 billion transistor design, 20 billion transistor design? Is it something you hire more electronic engineers? So, they will design engineer, they will build for you. So, you basically hire more people, you just so that you can actually parallelize the task and you do that. No, again it is impossible, or it cannot be achieved. This growth cannot be achieved by just hiring exponential number of design engineers, right. It achieve because of this design automation software, because of this evaluation of the electronic design automation software, this growth is possible, right. So, let us try to understand what is this design automation things I am talking about, right. So, in a chip, when you think about a chip or a IC, it consists of billions of transistors, right. So, these transistors are nothing but so in the layout they are MOS or CMOS or PMOS transistors. So, they are actually layout in physically, right. So, you basically if you think about the actual circuit, it has billion of transistors, right. So, this is what this transistor this is actually the physical chip, you cannot replace that, that is how this chip will work, right. So, what is this electronic design automation helps, and this is by do a design abstraction. So, what is this design abstraction? The abstraction comes that I am not going to look into my chip in the transistor level, I will try to look into little bit higher abstraction level, right. What is that? So, I will try to now visualize my circuit at the gate level, right. So, what is gate level? So, instead of transistor PMOS, CMOS, NMOS, I am now going to think about my circuit, which is a connection of the AND gate, OR gate and so on. So, all these logic gates, right. And what is that? So, one AND gate is something which will abstract probably 5 or 6 transistors. So, one behavior of 5 or 6 transistor probably I can combine and I can actually represent that as a AND gate, and AND gate I know this the behavior, right. So, similarly I can actually abstract a particular 5 or 6 transistors and I can actually abstract them as a say XOR gate and so on. So, this is how I can actually reduce the overall complexity by at least 10x, right. So, this is where the gate level. So, I do not have to think about say 10 billion transistors, rather I can now actually think about 1 billion gate level gates in the circuit. Of a circuit consists of 1 billion gates, but how these things will done? This will do by a electronic design automation tool, right. So, this is what is the physical synthesis tool. So, the EDA software will do this conversion for me. I will visualize my circuit at the gate level and I will complete all these connections, interconnection, all the functionality I will implement at the gate level, which is at least 10x less complex design for me, and then I will rely this physical synthesis tool, they will convert those gate level circuit into transistor level circuits, right. So, that is something is the design abstraction, but still as I mentioned this 10 billion to 1 billion, that is still not possible to handle, right, it is physically. So, then we should think about more abstraction, right. So, we go to one more higher level of abstraction, and that is called register transfer level design, which is called RTL. So, in the register transfer level behavior, I am not going to bother about how a adder is implemented, how what is the circuit of a multiplier. I will just represent my whole circuit as a transfer of register values, right. So, each that means at every clock which particular register getting updated by the value of which registers, right. So, I am going to write my behavior like R1 equal to R2 plus R3 and so on, right. So, say R4 equal to R2 star R3. something like this. So, I actually go, I do not have to bother about the detailed implementation of AND gate, a mux, demux or say multiplier. What I am going to just write that there is a full adder, right. So, I will draw the circuit like there is schematic. So, instead of a whole complex circuit, I will just put A and I will just put A, B and C. So, this is C is nothing but A plus B and so on. So, this whole design complexity of addition operation or the multiplication operations, those things now getting abstracted out. So, in the RTL level I will get more reduction in the design complexity. So, it may be say 1 billion to at least again 10x design, if not more, at least we will get a advantage of 10x size reduction. So, it may be say around 10 million now. So, that is how this abstraction goes to the register transfer level, and again I have synthesis tool or the EDA tools which is called logic synthesis tool. So, that particular tool actually convert this register transfer level to gate level automatically, right. So, in industry, EDA industry, in the electronics industry, people try to design circuits in RTL. That is the entry point of the circuit, because that is how this is the highest level of abstraction, right. So, you do not are considering the whole gate level thing, this is the highest level of thing. But is it so that as I mentioned, the 10 million line of code is still feasible? It is something sometime getting difficult once the size of the design is getting increased, right. So, again, so that is where we need to go more abstraction level, right, and that is where this particular course comes into picture, that let us go to one more abstraction level. So, we have a high level of code which is C, C++, and then you actually use, again you develop some software EDA tool that will convert this high level code into RTL code, and that is what is called this high level synthesis code tool, high level synthesis, and that is where I talked about this course. This is where this course is particularly poised in, is that this is how we actually develop a VLSI design from a high level code written in C or C++, right. So, that means we are going to go into detail of this tool, how this particular tool converts this high level code written in C, C++ into a equivalent register transfer level designs, and what are the process, what are the things we have to cover, that particular things we are going to cover in this course in detail, right. So, let us move on. So, I mean, I hope you probably understand that what is the importance of this design automation. Obviously, the shorter design cycle, right. So, we understand that if we just write a code in higher abstraction level, the size of the code is less, and hence we will need a less time, because the tool automatically within minutes or seconds it can convert a high level design into a low level design. It might take maximum hours, not days or months, right. So, whereas if you have to develop certain things in gate level or transistor level, that might take years, right. So, obviously, if you develop in higher abstraction level, your overall time to develop the whole IC will be less, right. So, you have a shorter design cycle. So, the biggest advantage is the design space exploration. So, suppose you want to develop a general purpose processor, and then you try to develop a processor which is very fast. It will work on say some 200 megahertz clock or 500 megahertz clock or 1 gigahertz clock, right. So, that means when you try to develop certain such processor, your objective is to optimize the speed, try to improve the performance in terms of speed. Now, I told you to develop another processor with the same specification, target for say power. I want to make it low power processor from the same specification, and now I told you to develop another circuit or another processor which is less area, right. So, I do not bother about the power or the speed. I want to I am bothered about the area, the size of the chip. I want to make a tiny processor for that, but it will from the same specification again. So, you understand that from a same specification you might have various design optimization criteria, and you have to develop different processor for the same thing. But what about in RTL? You have to develop things from scratch, right. You have to develop a power efficient processor, you have to develop a area efficient processor, you have to develop a timing efficient processor or the high speed processor, right. So, that is what is called design space exploration. So, doing this in RTL, it's a doubling, or it's the complete same effort for all processors. It's a huge time, right, something it is actually very difficult. Whereas, if you start from a C code and say in the high level synthesis, you have certain parameters, you just specify that parameters in the tool, that you do something for speed, you do something for area, you do something for power, and the tool automatically give you this different target processor in the RTL level within say minutes. So, that is a huge benefit, right. So, this design space exploration is actually possible only with this C based VLSI design, or through if you start the things at the high level behavior, not at the RTL level. So, that is again it is the biggest advantage. The other advantage is like fewer errors. Obviously, if your code is small, the chances of having manual error is something, human error is less, and obviously once you do it the higher abstraction level, your verification effort will be less, and then also you can actually apply different kind of optimization, more optimization at the higher abstraction level, right. So, these are the kind of advantage we will achieve through this design automation. So, I have, as I already discussed, that this electronic design automation flow is going through like this. Physically you have this layout. So, the layout has this I mean physical things like this metal oxides and all those things, and then there are multiple layers, and which is actually when you do this physically, you put these layers one after another based on the layout information, it will actually perform this transistor behaviors, right. So, actually it is layout this, but we visualize this as a transistors, and then from transistor we have the gate level thing, from gate level we have the RTL, and from RTL we have the specification or the high level C. This is what this EDA flow. So, here I just summarize this VLSI flow or the EDA flow like this. So, you have the specification, and then you write the architectural design, or you can write a high level design, and then you do the high level synthesis, you get the RTL, right. So, this is your C, Python, and then from this you will get gate level design using logic synthesis, and then you do this physical design. This physical design will give you the transistor level design, and then you actually do the fabrication, right. So, fabrication is something where you actually physically put this metal oxide layers one by one, which actually be based on the layouts, and that will give you the physical IC, right. So, this all is a software, they will just logically convert this, but physically you have to get the chip, and where this fabrication do this. Once the fabrication of the IC is done, then you just do the packaging, and you just do the testing and make sure your IC is actually functionally correct, and then you ship it to the market, right. So, this is what the overall VLSI design flow. So, I am going to cover these things very briefly, just to tell you what is the overall flow, but I am going to cover more on this particular topic, right, the high level synthesis in this particular course. So, as I mentioned, this high level synthesis or the C based VLSI design is something converting a high level behavior into a RTL design. So, in this RTL design you have so you can think about C code, which has basically a loops, if else, anything, function call, so many things can be there in the C code, and this tool will automatically convert into a RTL, and this RTL that is generated by a high level synthesis tool has a very specific structure. We will go into detail of that. It consists of a data path which actually execute these operations in the hardware. So, this data path consists of registers, memories, function units, and their interconnections, and there is a controller. So, controller determines that which operation to be executed in which clock, right. So, because these operations are executing, so there are many operations, you are not able to execute everything in a single clock, right. So, it is not possible. So, you have to basically decide that in the clock 1 I am going to say do this 3 operation, in the next clock I am going to do this 3, and then next clock and so on. In the next clock you are going to do this 4 operations and so on. Then this controller will say that it will send control signals to this data path to execute these first 3 operation in the data path in clock 1, in clock 2 the next thing, and so on. And also whatever the control flow, this while loop, so that these things will repeat for say 10 iterations and so on. if there is a if else branch and all. So, that will be controlled by this controller FSM. This is a finite state machine. So, then overall this combination of this controller and the data path is the register transfer level description, and which will actually execute the same behavior that is specified by a high level C code. Okay. So, this is something is the conversion, and in this course I am going to talk about the whole algorithm that is written inside this high level synthesis, how it actually works like this, and all other detail I am going to cover in few slides. So, because of this the huge advantage bringing the high level synthesis bring to this EDA design or electronic design, electronic industry. So, it is getting hugely popular day by day. So, you can see here almost all big houses, big EDA industries like Xilinx, Synopsys, Mentor Graphics, Cadence, they have a high level synthesis tool, which is a commercial tool now. So, everybody has their own high level synthesis tool, and they are getting popular and they are getting widely used in the industry, and we are getting commercial chip that is developed through this high level synthesis tool. It is getting used to develop a practical ICs in current in EDA industries. Okay. So, obviously, I am able to make sense that this particular course is very important in the sense that we can actually use this particular C based VLSI design or a high level synthesis as a gateway to come to this hardware from C code. So, somebody who is not expert in hardware concepts, or a person like me who is a computer scientist who can actually take a C code and automatically convert this into an hardware or a RTL, which I actually then further synthesize into logic synthesis, physical synthesis, and I can actually develop a IC from my code that is written in C. So, obviously, this is looks exciting, but there is one more very big advantage that this particular high level synthesis brings in the current context, and I am going to emphasize that in few slides. So, this is the era of specialized hardware, right. So, you might be heard of all this IP, right, intellectual property. One is for the JPEG encoder, say one something is for ML, one is for say a noise reducer, one is for say USB, one is maybe with some Bluetooth. So, for everything we have now a specialized hardware. But the question that you should ask, why we need specialized hardware, right. So, why we need some specialized software? Because we have general purpose processor and they are really powerful. If you think about a Intel processor which might have say 16 core, 20 cores or 32 cores, that means those number of processor and each of them is highly powerful. Why I can't do this image processing thing inside this general purpose processor? Why I can't do this image reductions or say noise eliminations, all those operations using a general purpose processor? Why the current trend is developing a specialized IP for every purposes, right. So, let us try to understand that. So, for that let us try to understand this overall the evolution again this EDA industry, that if you just this Moore's law which says the number of transistors doubles in every 2 years. So, you understand that every day you try to do more operation, so you need more resource, right. So, you need more transistors. So, and when Gordon Moore's he observes that the requirement is like this, that the number of transistor inside a chip is getting double in every 2 years roughly, right. So, now the question here is that, so if you have more transistor in a chip, so your size should grow, but it is not happening, it is happening in other direction, right. So, it is actually day by day we are getting a tiny chip, right. We have a mobile which is very just like this, and we can actually can keep it in the pocket, and which has billion transistors, right, which is running in some gigahertz speed. So, that means the size is shrinking and the transistor is getting increased, right. So, how it impacted? So, that is something characterized by this Dennard scaling, which says that so since the transistor is getting smaller, so we can actually put more transistor in the same area. So, the overall the power density does not increase, it stay constant. So, it is proportional to the area. So, as long as your area remains same, you put more transistor in it, since it is a smaller size, the overall power density does not increase that much, right. So, what does it imply? So, if you just combine this Moore's law with Dennard scaling, it means that you actually getting performance per watt is improving day by day, right, because you have more transistor you have the same power, but you are doing more operations. So, the performance or the operation per watt is getting faster, which is really good, right. So, is it something will continue? As the question is, will it continue forever? No, right, because if you see this particular diagram that so in around 2002 we have a 180 nanometer transistors, and now we are so we have 14 nanometer, we have 10 nanometer nowadays, and we can go till 7 nanometer. So, that means your transistor getting smaller and smaller, right. So, this say 10 nanometer is the distance between the gate and drain, that source and drain, right. So, which means your transistor getting very small, it very tiny day by day. Can it become 0? So, you have an end of it, right. So, you cannot make your transistor after certain time, it is not possible to small make it smaller after certain period, because which is not physically possible, right. So, but one more important aspect, that since you want to keep your power consumption fixed for a circuit, or you try to reduce it. So, since your energy per operation, so power is basically energy per second, and in this energy per operation is getting reduced, as I mentioned, this is the overall performance is getting improved. So, you need to run it faster, right. So, you want to do more operations per second. So, your frequency has to increase, and that is the current trend, that is to keep this scaling. So, we basically try to achieve the same power by significantly increasing. So, we try to drastically raise the clock frequency to keep the power consumption more or less same, or not improve that much, right. So, that means we try to sync the, we try to put more transistor into a circuit, and then you try to keep the power consumption same. So, basically you are increasing the frequency, but it has side effect, right. So, basically once you have this transistor become tiny, there is a current leakage and also problem of heat up, right. So, your chip can burn with this many transistor working on that. So, around 2006 or 7 we found a the end of this density scaling. We cannot just reduce these things, or you cannot pack more transistor into a particular design, I mean as much as possible, because you have the side effect of current leakage and this heat up, right. So, then we actually move to the era of multi-core design, right. So, multi-core processors. So, you know that instead of packing more transistor, you make it more complex, let us distribute it, right. So, instead of using one very powerful transistor, let us try to put more processors. You have use multiple core or multiple processors, all of them may not be that powerful, little bit lower powerful, and then you try to parallelize the whole thing, right. So, that is what this multi-core processor, multi-core era comes. So, you can see this diagram perfectly fine this. So, you see till 2005 or so, we have the single processor, right. As the number of transistor grows, so this is the number of transistor grows. So, as the number of transistor is going almost exponentially, so your overall power also getting increased, and then the frequency also, because you have to increase the frequency, and the performance also getting increased with the cost of higher frequency and higher power. So, by that time it reached almost 100 almost 100 watt, and then it is basically physically difficult to place more than, then we go to the era of multi-core. Now, instead of, so this is the number of core, instead of a single processor I am actually putting multiple cores, and see there are now at most we have a 64 core also in a particular circuit design. With that I am able to control the power consumption, because it is not growing like this. I am able to control the frequency, I can actually down the frequency, and also the sequential processor performance does not improve, because I do not want that, but the overall performance using the parallel processor increase, right. And I can keep this Moore's law live, because I am keep increasing the number of transistor in my design. So, is it something will continue, that I will put 32, 64, 120 and so on? It does not, there is a end of it, that also, right. So, this is given by this law, that this particular diagram told that how the speed up will happen with the number of processor. This is the number of processor, this is the speed up achieved. So, if you just double your processor, so your speed up might be double initially, but after some time it will flatten down, right. So, this is for 95% parallel, and this is say for 50%. So, after certain time, even if you increase the processor, you will not get that much of speed up, right. So, that means, so after certain point, and because it has now other overhead, right. So, that communications, I mean synchronization, so many other overheads comes. So, eventually you won't get those that particular advantage or the performance benefit. So, then is the roadblock that, I mean, initially I try to make a more complex chip and that has the end, and then we try to make more processor into a single chip, and now I am seeing that even if you put say more than 128 or something, you cannot achieve, I mean does not matter how many processor you pack into a single system on chip, you won't get much performance, right. So, is it a roadblock? I mean, is the end of this? No, right. So, because of, so what is the way out, right. So, we are almost kind of a roadblock, what is the way out. So, if you look into this human civilization, advancement of the civilization, so as the day progress we try to have a specialization, right. So, we are basically this civilization advancement happened through specialization, right. So, it means, so we have this doctor, we have engineers, within the doctor we have various specialists of doctors, and then in engineering also we have a very specialized of engineers, right. Somebody is electrical, somebody is computer science, somebody is mechanical, civil and so on. So, and then this specialization actually makes this advancement things happen, right. So, same thing actually these computers also follow the same path, right. So, it means instead of try to do everything using a general purpose processor, why not we try to think about a specialized processor which will do a specific job. So, it will be tiny because it is doing only one job, it is not the single processor doing everything. So, it will be a single specialized processor. So, it will actually do a specialized job. So, it must be very fast because it is actually doing that only that job, it is actually developed for doing one job. It will speed up the critical task because I know how to take care of certain difficulty of a particular job in that particular chip. It will reduce the power because it is doing only one thing. So, it has very small, it is not comparable with the general purpose processor, and also it will increase the energy efficiency. So, this is how this overall this evolution of this electronics design is coming, and if you see this some Samsung chip, Samsung mobile that we are using in modern days, it has there is a dual core processor in there which is kind of working as a manager. You have so many IPs, right, so many IPs, one is for say camera, one is for say JPEG, one is for say your interface, you have for USB and so many, right. So, it has many such IPs or intellectual properties or a specialized hardware that is actually fit into a system on chip. So, they are connected and they are just placed there to do a particular job, do quickly or accurately, and this particular the actual processor is actually managing all this, just coordinating with them and make sure that your whole chip is working fine, right. So, this is where this specialized hardware is something become extremely popular in modern days because to achieve the targets, right. And with this specialized hardware has advantage and disadvantage. So, whenever you have a general purpose processor, it is more flexible, right. So, you can actually have a processor which can do image processing, it can do some AI things, it can do anything, right. It can actually do some video coding, decoding and whatever, it can do anything, right, as long as you can map these things into his instruction set. So, it is more flexible, but it is less efficient, right. But when you go for the specialized hardware, it is more efficient, right. So, in the specialized hardware domain we have the DSP and then we have FPGA, and then ASIC is basically is very fixed, is a specialized tiny IC is for doing things a particular job, right. So, that means if you have a ASIC chip which will only can do only one thing, right. In the FPGA we can map, it is a reconfigurable architecture. So, I can map different design into this and it can actually execute that part. So, with this the advantage and disadvantage, but we do not need the flexibility, we need the efficiency in the current context. So, this specialized hardware is something is the trend in the current electronic design automation. And you can see that it's in the academic, in the startup, big companies like everybody try to develop a specialized chip, right. So, they try to develop a specialized chip for every purposes, and specifically this deep learning and this revolution of AI make this industry more useful, because you need more specialized architecture, specialized hardware, specialized processor for all these deep learning algorithms, right. So, is it something bad time also for these things, because you see there is a funny picture here is that the number of paper published in this ML domain, right. So, this is the archive paper only. So, you can see here almost 20,000 paper getting archived every year in the ML domain. So, it is not either too many applications, and if we try to develop this IC for all these 20,000s, I mean it is not something too much if you try to develop them, right. So, let us try to understand this from this table, that once you have a general purpose processor, if you just consider that is a speed up is 1 to 1, if you go for GPU, it is basically 50x improvement, and in FPGA it is almost 550 times improvement, right. So, this is the performance per watt also increase this way, right. So, it is almost 1000, I mean 1100 times faster than the normal processor in the performance in terms of the power, and also the design time in increase, because you can map anything into a general purpose processor, but here you have to develop the whole circuit. So, this is the kind of advantage where you have to look into, right, and where our this course comes into handy. Okay. So, now the question is that we have this many application, we need a specialized chip for all this application. So, is it possible to develop everything in RTL, right. So, the register transfer level, as I mentioned, still it is a hardware design, it has clock, it has multiple clocks, it has multiple signals like synchronous signals, reset, resets, it has memory, it has all this interconnection, you have to take care everything at this level. So, developing so many application or the so many IPs at the RTL level may be difficult, right, it is not impossible. So, there this course, this high level synthesis course comes into picture, right. So, instead of developing IP at the register transfer level, because all the application people write a AI application never in RTL, right, they always write in say TensorFlow, in C, C++, right, and then try to run it in a general purpose processor. What about this high level synthesis that will take those high level behavior in TensorFlow or say C, C++, and then you convert them into equivalent hardware, that will do a wonder for this, and we can actually quickly get IP which is specifically doing a specific job, right. And also as I mentioned that we can actually have different IP for different purposes, one is for say speed, power and area, right. So, that is where this particular course is so relevant in the current context, that we can actually take all this new developed ML and AI aspects, and then all this algorithm we can quickly take them and convert them into a specialized IP, which I can, or the specialized IC which I can actually utilize for faster execution of those behaviors, right. So, that is where this high level synthesis things comes into picture. So, here I just give an very high example that you want to just develop a counter. So, it is just a C++, right, C equal to C plus 1 in C. If you just try to write this in hardware, you have to have a clock. In after every process of clock, you have to, if the reset comes, you have to reset the things, otherwise you just increase it, and then you assign the output to this C, right, and you have to develop this registers and all those things, right. So, this is how we have to write the RTL, and whereas this is nothing but C equal to C plus 1 in the C, right. So, and then this high level synthesis tool take this and it will convert into this, and which is nothing but this circuit, and then this is the high level synthesis tool, right. So, this is where this particular course is so important, because we need now specialized architecture, we need a hardware acceleration, and for this hardware acceleration, because almost everybody write everything in the higher level in specification in C, C++, TensorFlow, and then this high level synthesis can convert those applications into equivalent hardware, which will be a very faster or efficient execution of this particular task in hardware, right, and which will give you more performance benefit over general purpose processor. Okay. So, this is where this particular course is so important, and I am very excited that I am going to cover many important things in this course, and this particular diagram again summarize that the use of this design automation, and specifically this C2 RTL, right. So, this is something I have already covered. So, in the context of machine learning and electronic design automation, there are two way of use it. So, the first use is something like that we have the EDA algorithms. I told you that I have a C code, and then you convert into RTL using high level synthesis tool. I have say RTL code, I want to convert into gate level design using logic synthesis tool. Can this machine learning tool help? Machine learning algorithm helps there, right. So, that is one way of looking into application of ML in this EDA. Similarly, you have one more direction is that, which is more relevant for this course, is that can this EDA help to have a performance improvement of the machine learning algorithms, right. That is, can we have a hardware accelerator for machine learnings using this EDA tools. And if you look into this current context, there are wide variety of such applications are coming, and it is a very popular area of research, and in this particular area of research this high level synthesis is more useful and very relevant in this current context, right. So, now I hope I can convince you that this particular course is something very exciting, and it is very important to develop a hardware accelerator for the modern day application like machine learning and deep learning and any other application as well. So, I am going to taught this particular course keeping into mind in the current research in context, and specifically I am going to cover these are the topics in this high level synthesis. The first thing we try to understand how this C code is converted into RTL, how a untimed code become a timed code, how to do all those things, right. And then what are the steps involved here, right. So, what are the sub steps of high level synthesis and how we can logically convert these things step by step into an RTL. So, I am going to cover these things in detail, all the algorithm involved here, what are the popular algorithm, what are the important algorithms, all the algorithms useful in this context I am going to cover here. And then there are one more very important topic is that if you write any code and you try to develop a hardware, that may not result in a good hardware, right. So, in efficient hardware, sometime you have to keep your mind keep it in mind that this code will be converted into hardware. So, you need to write this code which will be suitable for hardware, right. So, you have to write a hardware efficiency code, how to write that. So, if you know that this, if you write this, it is bad for hardware. So, I am not going to write this way, I am going to write the code in different way. So, that something is something I am going to cover again, that how to write C code for efficient hardware generation. Then I am going to cover the topic like this. Once you have a C code, you have a GCC compiler, LLVM compiler, they have 100 of optimization, right. So, they take a C code and then convert into another optimized C code which is applying various optimizations. I hope you are aware of those optimizations. Now, since I am converting this C code into hardware, why not taking the advantage of this optimization which is already implemented, right, widely available. So, I am going to see what is the impact of this compiler optimizations in the hardware. Is it something good, is it something bad? If something is good, I can take them automatically because it is already there, right. I have a C code, I can just first apply this GCC to optimize it, and then optimized version I am going to convert into hardware, right. So, this is I am going to cover then how this common compiler optimization help to improve the circuit performance. I am going to cover that. I am also going to cover this hardware acceleration for machine learning algorithm, which is something very important in the current context. And also there is another important is this security, right. So, nowadays the security is very important in every context, and hardware security specifically is very important, that say in the current context you know this finally this fabrication happen by a third party. That means, you develop your chip, you develop the layout and you give the layout to somebody who do only the fabrication, because fabrication is very costly, not every electronic design company can afford that. Okay. So, now the third party has access of your very intellectual property, right, and they can actually check it and they can overproduce it, they can have a IP piracy, they can develop their own taking this, or say more dangerous thing, they can actually add some trojan into your circuit, malicious code into your circuit, such that once you ship it, it will malfunction, it will do something, right, or they might leak certain secure data to them. So, there is a huge chance of having all these things, right. So, to stop that, you have to develop a hardware, even if it goes to third party, they are not able to understand this. Even if they actually get this layout, they can't use it because of certain thing, you lock the circuit, you make this secure, right, or they are not able to do anything change on this, right. So, that is where this hardware security is very important in the current context, and I am going to cover that part also, that how to develop a secure hardware through high level synthesis, that is also very important in the current context. And then I am going to talk about this verification of this RTL, because once you convert a C code into RTL, you have to make sure they are functionally correct, right. So, your RTL is exactly functionally correct with your input C code, and that is where I am going to talk about the how do you actually check that, the equivalence checking between this C and RTL. And then also I am going to cover, since it is a VLS C-based VLSI design, it is not only the RTL and then how this RTL is converted into gate level code is converted into transistor level and so on. So, I am going to cover the overall EDA flow, but again it is briefly, because this is the rest of the part is kind of very conventional. I am going to cover very briefly about this overall EDA flow. And also I am going to cover, this is also important, that in the RTL level there are many optimizations available. So, and also inside this high level synthesis tool also there are many optimizations available. So, what are the optimizations available and how to utilize, what is their impact in the generated hardware. So, I am going to cover this design optimization things in this course as well. Okay. So, the prerequisite, I am expecting that you have very basic knowledge of digital design. You should understand what is register, clock, what is gates and all. Just having a basic knowledge is fine. I am not expecting that you have a very depth knowledge about that. So, just having a basic knowledge, giving a Verilog code, you should understand, oh, this is this, nothing else, right. So, that is sufficient enough. And also in this particular course, because it is automation, you need to be familiar with certain algorithms, specifically certain graph algorithms like graph coloring, click partitioning, shortest path, and then sorting, searching and all those things, right. So, you should have a basic knowledge about the data structure. That will help, because sometime I want to take this, say, some scheduling problem or say particular optimization problem into a, say, graph coloring problem. So, and then I try to solve using graph coloring, right. So, I am going to map this problem into very well known computer algorithms and then try to solve the problem. So, having a basic knowledge about this data structure algorithm will help you to understand this course, but I will try to make this course self content. Wherever I need, I am going to give emphasis a particular algorithm, will explain the algorithm, then I am going to use this. So, I mean, hope it will not create a big obstacle for you to understand the course. 2 textbooks I am going to follow in this course, primarily this D. Michelis book on synthesis and optimization of digital circuits and this parallel programming of FPGA. These 2 book I am going to follow, and I am going to follow various conference and journal papers, because not everything is has a book on this, right. This is a very advanced course, and then it has many things which is already still research papers. So, I am going to cover many such important conference and research papers in this course. There are other reference books like this Advanced FP Design by Steve Kiltz, Keshav Pari for this various optimizations, Gatsky's book on high level synthesis, and this high level synthesis blue book, right. So, these are the books I am going to, and most of the books are actually available. So, you can have it. Some of the slides I have taken this, specifically this graphs, plots, I mean I have taken or adapted from these 2 professor. I am thankful to them for this content. So, with this I conclude this lecture. I hope you will learn lot of things in this course, and it will be fun for you attending my subsequent lectures. Thank you.